All right. So, good evening, everyone. My name is Aditya, and my co-authors for Maple are Himanshu, Diksha, as well as Dr. Mamta. So, Maple stands for masking words to generate blackout poetry using sequence-to-sequence learning. So, this is an outline of what we'll be going through today. I'll quickly introduce to the concept of blackout poetry, followed by the methodology that we'll be doing. Then we'll talk about the workflow. And finally, we will compare our results and do an analysis of our results. So what exactly is blackout poetry? So a lot of you might not be familiar with this concept. A blackout poetry is essentially one of the most recent formats of poetry, which has quickly gained attraction since about 2009. So in blackout poetry, a passage is taken, let's say from a book or from a page, and certain words are blackened out, except for just a few words here and there. And when you actually combine these words in the order in which they appear in, you will actually obtain a poem or a phrase from this given passage. So this poem that is obtained is called a blackout poem. And one of the first instances of blackout poetry was actually performed on the New York Times paper, and it was performed by Austin Kleon. He used to actually take almost every edition of the New York Times, and he used to sort of blacken out words and form poems and publish them. And in fact, the New York Times website actually has a certain web page which is dedicated to him for this purpose, where you can actually go and click on different words in a given newspaper article to generate your own blackout poems. It's really cool. You guys should really check it out. So this is an example of what I was talking about, where an example like this is given, where you take out a passage and you essentially just pick out random words from the passage that sort of form a poem or sort of form a phrase that conveys any meaning. The first one is more essentially the earlier forms of blackout poetry, where you just blacken out everything else. And the second one is slightly a more artistic thing, where you add in a few other artistic elements to make it look nice. So we were trying to find a way to automate this process. And when we did our survey, we found that there have been pretty much no real approaches to this thing, except for one given approach, which was performed in 2016 by someone named Lisa Daly. What she had essentially done is during the National Novel Generation Month, which is NaNoGenmo. This is an event which is directed at language generation, automated means of language generation. So Lisa Daly had essentially generated blackout poems from any given passage that is fed to it. So, but the problem here is the approach which was used random sequences of words which should sort of generate a poem. So it essentially relied on pattern matching. So it would be fed in with a few grammar rules, such as, let's say, verb followed by an adverb and so on. And it would pick out the first matching sequence from a paragraph that fit this particular construct. And while this did work for a few cases, we realized soon that this approach is very restricted, since firstly, it picks up only the first set of words. And secondly, there is no way to essentially check if the sequence is correct or not. And this is an example of the poem that was generated using her method. As you can see, in the first case, it absolutely failed to generate a poem. And in the second case, the poem isn't really very well formed. It's just four words that have been put together that form, or rather that match a sequence. So what we try to do is we try to use sequence to sequence learning to tackle this problem of blackout poetry generation. We are trying to beat Lisa Daly's method in terms of correctness, human nature, as well as readability. We look at two major natural language processing techniques in terms of sequence to sequence labeling. The first being abstractive summarization, and the second being sequence labeling. So let us quickly go through the workflow that was followed. So one of the first issues that we face is that there was no publicly available data set for doing this. There are a large number of poems that are available on online archives, but there is no data set that actually is used to perform blackout poetry generation. And so we had to resort to using Lisa Daly's method of synthetically creating a data set. Now, while this did hamper our performance, you will soon see that it did improve upon the model that already existed on. So instead of using a random set of rules that Lisa Daly had proposed, we use statistically found rules. So what we do is we essentially find a large number of short poems and phrases, and we find the part of speeches, grammar sequences for these, and we pick up the top K repeating such sequences. And the reason we do this is because since we know that these part of speech grammar sequences have been used in poems, these are probable sequences that can occur in sentences. From this given set of sequences, we do the same pattern matching that was involved. But instead of picking up just one sequence, we instead pick up all possible sequences from the passage. Later, we also do a little bit of pre-processing where we remove any kind of bad symbols, anything which is not a character or a punctuation. So to give you an example, the part of speech grammar rules that we extracted are found in the left table. The dataset attributes have been provided here. As you can see, the number of total passages that we had were about almost 17,000. And upon splitting into train and test, those were the numbers that we obtained. And as you can see, the generated blackout poems using the statistically found technique is better. It was able to generate something for the first passage, and the second blackout poem, although not really a well-formed poem, was able to generate something better. So the evaluation metric that we propose is perplexity scores. So we don't really have a proper, quantitative metric to evaluate blackout poetry. So we simply use perplexity to analyze how well-formed the poems are and how probable the poems are. And secondly, we perform a very simple Turing test where we created a questionnaire, and we had 8 human written poems and we had 8 machine generated poems. And these were shuffled together and shared with participants in the age group 18 to 22. And we had about 120 responses, and we're happy to say that we did actually pass the Turing test. So after the model actually generates an answer, there is a post-processing step involved where we simply clean up the sentence by adding back any kind of punctuation that was missed out, or capitalizing some words which were turned into lowercase while training the model, to add more grammatical structure to it. We again add back the article that was skipped. So the first model that we use is abstractive summarization, and this model is actually an experimental model that we tried out to analyze, or rather to compare the performance with sequence labeling. We use a simple encoder decoder network with attention to perform the summarization. A simple embedding layer was used, which used fast text embeddings which was trained on the passages themselves. It was simply trained on 10 epochs because we realized very quickly that this approach won't really work out, and we were able to almost hit the lowest loss we could obtain with just 10 epochs. It was optimized using the Adam optimizer. And quite obviously, this model is not suited for blackout poetry generation because abstractive summarization does not really pick words from the passage. And these examples are not examples of blackout poetry. We found that in pretty much almost 90% of the cases, it did not pick words that were in the passage themselves. And if it did pick words from the passage, they were not really in order. So no, this approach didn't really work out. However, sequence labeling is an approach that did work out pretty well, and this is the model that we do propose. So we treat the problem as a simple sequence labeling problem, where the words chosen are the words which are to be labeled as a one or any other label. We use a transformer-based architecture for this, and we tested on 2 primary models, that is the BERT and the Roberta models. So to give you an idea of how they perform, these are the results as you can see. And firstly, it did follow the essential rule of blackout poetry generation. That is, it was able to pick out words from the passage in order. So that was the first, the first thing that told us, okay, we were going in the right direction. And secondly, the results that we obtained were, of course, better than abstractive summarization. But once we compared them with Lisa Daly's results, we found that they are actually better than even those results that had been obtained. And as you can see in the 2 tables that have been provided, So BERT and Robota, they work pretty much almost the same, although BERT was found to be more consistent across the 15,000 passages that we had. So a comparison of results that we are obtained. So our blackout poems, which were done on sequence labeling, had a significant improvement over Lisa Daly's approach. The average perplexity was found to be lower, and this indicates that that we had generated more probable poems compared to Lisa Daly's. Although there's one drawback, that is not neither of the two models that we had were able to consistently generate good blackout poetry. There were quite a few examples here that in which the results weren't really coherent and the results were really poor in a few cases. Although when you do compare BERT and Robota, BERT was found to be way more consistent compared to Robota in this particular task. So now looking at the Turing test that was performed, what we essentially found is that a few of the machine-generated poems were labeled easily, and people were able to quickly identify that it was quickly able to identify that this poem was written by a machine. Although the number of incorrect predictions made by the audience was higher, it was higher by only a very small margin. So essentially, that means that although the models were able to pass the Turing test, they were barely able to pass the Turing test. The number of unsure predictions across all the poems remained roughly the same. So this is to give you an idea of all the 8 poems that are machine generated. We haven't attached the human generated poems here because we are focusing on the machine generated poems. So as you can see here, in most cases, uh, the human votes are higher, which means that we have been able to pass the Turing test. But there's another thing which you can note, which I had highlighted, is that the difference in votes is not really higher by a big margin. It's just a few votes here and there, except for the first case, which is a significant difference. So this is a distribution of the predictions for the machine-generated poems. So as you can see, for the machine-generated poems, 52.7% of them thought that they were human, whereas 35% of them thought that they were machine. And the number of unsure was about 12%. And attached next to the pie chart is a simple confusion matrix of the predictions that were made across both classes. So concluding this, yes, it is possible to generate blackout poetry using sequence labeling techniques. Although all the models are highly consistent in the results, we see that the transformer is the best working model, and we believe that maybe with a little bit more fine tuning and with a bit more experimentation with different model types, we will soon be able to generate much better blackout poetry. The other thing that is a big drawback is the fact that our performance is greatly hampered by the data set that we have, because it is a synthetically obtained data set. It is a data set generated by us. And we feel that in case if in the future, if there is a well constructed blackout poetry data set, then we should be able to generate much better examples of blackout poetry. And that is pretty much it for Maple. I will be answering the questions. I'm really sorry I could not get to the questions.
Thank you very much for the presentation. I think we have about 3 minutes for questions.
Yes. So there are 2 questions.
Yeah, if you can read out the question.